We'll solve another Leetcode problem. 3326 minimum division operations to make array non-decreasing. So let's first try to understand what we are doing. So we are giving an integer array nums. So the nums are going to always be positive integers. And the maximum value is going to be 10 to the power of 6. So this means maybe we're going to use construct algorithm to solve the problem. I mean, we're going to construct all the possible cases and then we're going to solve it one by one. So any positive divisor of a natural number x that is strictly less than x is called proper divisor. So let's just use example 25. So it has divisors of 1, 5, and 25, but 25 is not inclusive because that value is going to be less than 25. It's going to be less than this value x. So 1, 5 is okay. So for example, 2 is a proper divisor of 4, and while 6 is not a proper divisor of 6. Yet 6 is not a proper divisor of 6. So you are allowed to perform an operation any number of times on nums. So for example, if a nums is 125, we can do any kind of operations. We can divide it by 5, it becomes 25, or we can divide it by 5, again it's going to become 5. Yeah, we can do any number of times. Where in each operation, you select any one element from nums. So you select any element from nums. For example, we're going to select 25. Yeah. And divided it by its greatest proper divisor. So what is the greatest proper divisor? So for example, 25. The greatest proper divisor is 5. So it's going to be divided by 5, and then we're going to get a 5. Yeah, so this is the meaning. So you are allowed to perform any operations. You are allowed to perform an operation any number of times on nums. So we are allowed to perform an operation any number of times on these nums. Where in each operation, you select any one element from nums. So for example, we're gonna in each operation, this is one operation, we're gonna select any one element from nums. For example, this is an operation 25. And divided it by its greatest proper divisor. So 25 divided by 5, it's going to be 5. So this means we've already finished the operation. But for this 5, we cannot do any more operation. Yeah, this is something very confusing. So for one number, we can only do one operation instead of many operations. So this means for this nums array, we can do any number of operations, but most of the operations should be less than or equal to the nums array. We can do this operation or not, but if we want to do this operation for this number, we must do one operation instead of many operations. We have to understand, yeah. You are allowed to perform an operation any number of times on nums. Yeah, it is said any number of times. We should know that, yeah. Where in each operation, you select any one element. This is one operation. You select any element. For example, this is 25. And divided it by its greatest proper divisor. So it's going to be divided by 5. If it is divided by 5, greatest proper divisor, so what is going to be the result? Result is 5. So this result is the smallest prime factors of 25. If you don't believe it, let's try another example. For example, we have 9. So 9 divided by 3, it is 3. 3 is the smallest prime factors of this 9. Or maybe we're going to use another case, 8. 8 divided by 4, it's going to be 2. 2 is the smallest prime factors of 8. Yeah. So this means we only need to find the smallest prime factors of this number, and then we can solve the problem. If it is possible after all the operations, it is in increasing order, so that is okay. Otherwise, we're going to return a -1 if we didn't find. Yeah. Now let's just write some template. So I'm going to call it E prime factors. There's a lot of template, but this is only one case. So I'm going to prepare a factors. I'm going to call it default dict, it's going to be a list. And then here is similar like the Aristotle's algorithm, just similar like how can we find the prime numbers. This is for finding prime factors. It is similar. So we're gonna prepare a prime array. It's gonna be false times 2 plus true times n minus 1 for I in range from 2 to n plus 1. If this is a prime number for this I, for j in range here gonna be a little bit different, so it's gonna be I to n plus 1, and the step gonna be I, and this prime j gonna equal to false, and here we're gonna append it, so factors j gonna append the I. Let me check. Yeah, and then we just need to run this function, so let's just run it, and finally we just get a factors dictionary, and this is exactly what we need. So this one going to be 10 to the power of 6, and because the maximum number is 10 to the power of 6, we just needed to know this number. So this is just the preparations. After the preparations we can just solve the problem. Actually it is just a little bit coding. The length of the nums array, let's just prepare it, and then we're going to check from the right to the left side, because this is the greedy idea. So for example, this is 7 is okay, we're gonna ignore it. What about this 25? We can reduce it to 5 is okay, 5 is less than 7, it is okay. And now how many operations? It is only 1, so we're gonna return 1 operation. What about the second example? So inside the second example, this is a 6, but this 7 is more than 6, but we want to reduce it. Is there any prime factors which is less than 7? There's no, so it's going to be 7. 7 is more than 6, so it's going to be -1 because we cannot find it. Yeah. Now we're going to write the program in just like this. So for I in range from n minus 2, -1 and -1. So we're going to just loop through it from the right to the left side, and then we're going to check one by one. If nums I more than nums I plus 1. So this means we need to reduce the number. So the nums I gonna equal to factors of nums I, and this is gonna be an array, and we're gonna choose the first number. Yeah, but what if there's nothing inside the dictionary? We have to check. Yeah. So after the if check, let's just imagine if this nums exist. So if nums I is still more than nums I plus 1, let's put it. Let's put it here. If nums so we're gonna return a -1. Otherwise, we're gonna update the result, and finally we're gonna return this result. So let's just set this result to be 0 from the beginning. So this is just a counter. Yeah. Now we need to know if we can update this nums I. Yeah. So currently from here, if this nums I is more than nums I plus 1, and we need to check if it exists, so we're going to use a length of a factor. If length of a factor nums I is more than 1, so this means, so for example, if this number is 7, inside what do we have? We have 1 and 7. Let me think about it. Yeah, for this 7, the prime factors, we don't have 1. Let me just make it right. So we have a prime factor of 7. So for this 7, according to our algorithm, because everything is we're gonna include itself. For example, 7, the prime factors are gonna be 7, but there's no 1 because it is prime factors according to our calculation. So we're gonna check if the length is 1, we will ignore it. But if the length is more than 1, we're gonna choose the first number. Yeah. So if it is more than 1, so the nums I gonna equal to the factors nums I, and we're gonna choose the first number, and then we can check it from here. I think we can check it from here. Yeah, and then if this nums I is still more than nums I plus 1, we're gonna return a negative 1 immediately. Yeah, if everything's okay, we're gonna update the result. Let me just run it to have a basic check. It didn't work. Yeah, it means something wrong with my coding. Let me think about it. If nums I I just solved it. I believe I can solve it. I think it's just a little bit difference of my coding. Maybe let me just print out this one. I just want to check if everything's okay for my factors dictionary. I just want to have a basic checking. Oh, I cannot print it out. Maybe I'm gonna check factors. Maybe let's say just 25 maybe. Let's just check what is inside. For this 25, let's check. It's gonna be 5. Factors 25. So let me just check the factors 25. So for factors 25, it is 5. I don't believe it should be 5, but let me just think about it. So the factors j gonna append I. Yeah, I think it is because it is a prime factors, so it's gonna be only it will be 5. Yeah, because for this calculation it is only the prime factors. So what about 7? Factors 7? So yeah, it is 7. Yeah, let me think about how can I run it, write it. So if nums I is more than nums I plus 1, maybe I will not check it. Let's just put it like this. Nums I gonna equal to factors nums I. We're gonna choose the first. We're gonna choose the first factor. Yeah, I can pause for some testing case, but of course this is not okay. The third one. This is 1111. So our result should be 0 instead of 3. If nums I from here, we're gonna reduce this one, and we're gonna only choose after removing the last one, we're gonna choose the first one. And from here, we're gonna choose the length. If length of this one is more than 1, we're gonna update it. Yeah, I still don't know why my previous coding works and currently this one didn't work. Let me check my previous coding. It's a little bit strange. Maybe I didn't understand exactly what I'm doing. I think I write exactly the same, but something is wrong. Yeah, I think something wrong is about here. My updating of the result, it should be here. If this is more than nums I plus 1, and if I didn't return -1, and then I will update the result, but I put it outside this if checking. Definitely it is wrong. Let me just run it. Yeah, but there's still something wrong. Yeah, this is confusing. I don't know why. If nums I is more than this one, if length of the nums I more than 1, I'm gonna update it. Yeah, I don't know. Yeah, let me just check what is wrong with my coding. Yeah, normally I should I don't know. Yeah, let me just copy and paste. Maybe it is just these areas, but I cannot find. No. Yeah, it means my coding from this area should be okay. Maybe the factors writing is wrong. Let me just copy and paste. I don't know. Yeah, it seems my preparations is wrong, and I don't know why. Let me just have a check. So I prepared the factors, and I prepared the prime numbers. This is true to n plus 1 if primes, and for j in range primes to false and j append I. Yeah, I think it is okay, but actually it didn't work. Yeah, I don't know why. Yeah, it seems a little bit different. Yeah, I think I know why. Actually, my coding, I did something wrong, but actually I get the yeah. Actually, I passed. Actually, I didn't mean it, but actually I passed. And this is something strange. Yeah, I checked the primes I. Actually, If I don't check it, I can pass, but actually this is wrong. Yeah, because every time it's gonna be true. But in this case, let me check what is inside my primes. What is inside the factors 25? Yeah, let's just check what is inside. I think it's gonna be 5 and 25. As you can see, it is 5 and 25. Yeah, actually for my coding, I want to have this 5 and 25 instead of just prime factors. I want to have all those factors. 25 is also a valid factor. Yeah. So actually, I don't need to have this this tag. I just need to find all the factors. Yeah, let me just change it. So from here, for I in raise 2 to n plus 1, and for j in raise I to n plus 1, I don't need to set the true or false. I just need to prepare all the possible cases, and I don't need to have this one actually. Yeah, and let me just check another case, maybe 100. Yeah, so this is just checking for all the possible cases, all the possible factors. As you can see, for 100, we have something like 2, 4, 5, 10, 20, 25, 50, and 100. Actually, this is exactly what I need. Actually, this is something wrong, but actually it passed, but actually I don't need to make it so complicated. Yeah. Now we're gonna write it like this. So I will not call it E prime factors. I will just call it maybe E factors. It's gonna be all the factors. Yeah, because in this way, actually I prepared all the factors. So for example, 100, this is all the factors, and this is just easy to write. So from 2 to n plus 1, and for example, this is a j. While we are checking this number, we're going to prepare all the possible I. So for j in range, so for example, this is a 2, and j is a 2. So for 2, we're going to have an array of 2. What about 4? If this j equal to 4, so this factor is 4, gonna append a 2 before, and then it's gonna append another 4, I believe. Yeah. So actually, it is just like this. So in this way, definitely we're gonna include the number itself. So this means we need to remove the number. So let me just check. Actually, for here, we don't need to write it like that. It is not necessary. It can still be simplified. Yeah. If this number is more than this one, and if the length is more than 1, we're gonna choose this number. If it is equal to 1, definitely we will not do anything. I think this is okay. Now it will be simple enough. Yeah, let's just check if it works. Yeah, now as you can see, it works. And now let me just submit it. Yeah, so the idea is very simple. So for example, for 100, as you can see, it passed and it's pretty fast. Yeah. So let me just explain the idea a little bit. So for 100, definitely we want to find the maximum greatest proper divisors. It's going to be 50. So 100 divided by 50, it is a 2. So this is exactly what we need. For this 25, definitely we're going to divide it by 5. It is 5. Yeah. And inside this algorithm, definitely we can find all the possible cases. So we're gonna start in from 2. Yeah, let me just check all the numbers. It's gonna be starting from 1. Is there any other edge cases? Because the numbers are gonna be starting from 1. Yeah, but for 1 itself, there it's gonna be just include a 1. But even we didn't prepare it. Actually, for 1 and 1, it didn't work. Yeah, because it includes itself, actually it should be empty. And for our case, it is exactly like the empty case, so we can ignore that. Yeah, this is just something we need to take care because we are starting from 2, not 1. But it is still okay for our algorithm. Yeah. So this means we're gonna include all the factors from this I. If that is possible, we're gonna include all of them. And as you can see, the coding is also very simple, just 3 lines of code, and then we prepared everything for our calculation. And the time complexity is, let's say it is just ON. As you can see, this is just a for loop. Here is also a for loop. Although you can say this is a for loop, this is another for loop, but you can understand it as n times, let's say n times log n. So this is n log n. So this is why it works, otherwise it cannot pass. And this is ON time, so the time complexity is n log n. I believe. I think that's all about it. And thanks for watching. See you next time.